We live our lives by the clock. We feel time as a constant forward-moving river pushing us from breakfast to dinner, from birth to death. It feels like the most real thing in the world, the ultimate force that governs our existence. But when we ask physicists what time truly is, the solid ground beneath our feet begins to tremble. The smooth-flowing river we perceive dissolves into a series of profound puzzles, paradoxes, and perhaps the greatest illusion our consciousness has ever created. Our modern understanding of time begins with Albert Einstein. Before him, we imagined time as a universal drumbeat ticking at the same pace for everyone everywhere. Einstein's theory of general relativity shattered this idea. He showed that time is not separate from space. Instead, they are woven together into a single four-dimensional fabric called space-time. This fabric is not a rigid stage. It is a dynamic, active participant in the universe. It can stretch, bend, and warp. What causes it to warp gravity? A massive object like the sun doesn't just pull the Earth with an invisible rope. It creates a deep dent in the space-time fabric like a bowling ball placed on a trampoline. The Earth isn't being pulled, it's simply rolling along the curve created by the sun. This warping doesn't just affect space, it affects time. Time is elastic. If you are near a very strong source of gravity, like a black hole, time itself slows down dramatically compared to time for someone far away. This isn't just a theory. Our GPS satellites, which orbit high above the Earth, experience time slightly faster than we do on the surface. The satellites' clocks must be constantly corrected to account for this relativistic effect, or our navigation systems would fail within minutes. Einstein proved that time is not absolute. My now is not necessarily the same as your now. If general relativity makes time flexible, the other pillar of modern physics, quantum mechanics, almost makes it disappear. When we zoom down to the smallest possible scale, the world of particles, probabilities, and quantum leaps, the equations that describe reality don't seem to care about the direction of time. The fundamental laws governing an electron or a photon work just as well if time runs backward as they do when it runs forward. The equations are time symmetric. They show no preference for past or future. This presents a massive contradiction. The micro world of quantum physics is symmetrical, yet the macro world we live in is clearly not. Eggs break, they don't unbreak. People grow old, they don't grow young. We remember the past, not the future. So where does this one-way street, this arrow of time, come from? The best answer we have for this deep mystery is a concept called entropy. This idea comes from thermodynamics, the study of heat and energy. Entropy is simply put a measure of disorder or randomness. The second law of thermodynamics is a fundamental rule of the cosmos in any closed system. Entropy disorder will always increase. This law is the only major principle in physics that seems to have a built-in direction. This is what we call the arrow of time. The universe, it seems, started in a very highly ordered low-entropy state at the Big Bang. Since that initial moment, it has been steadily unwinding like a clock spring, releasing its tension, moving from a state of perfect order toward a state of maximum disorder. A whole egg is an ordered system. A broken, splattered egg is a disordered system. A hot cup of coffee with all its heat energy concentrated in one place is more ordered than a lukewarm cup that has spread its heat evenly into the surrounding room. Time might just be our perception of this unfolding process. The past is simply a state of lower disorder, and the future is a state of higher disorder. The river of time only flows in one direction, because that is the direction of increasing entropy. This leads to an astonishing and counterintuitive idea: time may be an emergent property. What does that mean? Think about temperature. A single water molecule does not have a temperature. Temperature is not a fundamental property of one molecule. Instead, temperature is a word we use to describe the average speed of a huge group of molecules bumping into each other. It is a collective property. It emerges from the crowd. Many physicists now believe time is the same. At the most fundamental quantum level, there may be no time at all. But when you get a vast complex system like a universe or a human brain or a cup of coffee, this property we call time emerges from the statistical interactions of all its parts. It's a large-scale effect. Just as temperature is about the statistics of motion time may be about the statistics of entropy. The search for time's origin has recently taken an even more bizarre turn, leading to one of quantum mechanics' strangest features: entanglement. Quantum entanglement is the spooky action at a distance that Einstein famously disliked. It's when two particles become linked so deeply that no matter how far apart they are, even on opposite sides of the galaxy, measuring one instantly influences the properties of the other. Some cutting-edge theories propose that space-time itself is not fundamental. Instead, space-time emerges from entanglement. In this view, the pixels of our reality are not points in space, but bits of quantum information. The geometry of our universe, the very fabric of space, and the connections within it are created by the patterns of this entanglement. Time, then, would be the story of how these entanglement patterns shift and evolve. The physicist Carlo Rovelli offers a beautiful and poetic perspective. He suggests we stop looking for a single master, time, that governs the universe. He argues that time is a product of our interaction with the world. We are limited in our view. We don't see every individual atom, we see eggs, cups, and people. We blur our vision, and in doing so we create a statistical averaged-out story. For Rovelli, time is ignorance. It is the measure of change relative to other changes. A clock ticks relative to the sun's position. Our hearts beat relative to the clock. Time is this web of relative events, a story our brains weave to make sense of the world. Perhaps the most brain-bending and profound idea of all comes directly from Einstein's work. If time is just another dimension like length, width, and height, then it must be treated as such. This leads to a theory called the block universe. Imagine a movie. When you watch it, you experience one frame at a time, creating a story that flows and has a past, present, and future. But a person holding the entire reel of film can see all the frames at once. The beginning, middle, and end all coexist. The block universe model suggests that reality is that entire reel of film. The past, the present, and the future all exist right now simultaneously. The dinosaurs, your breakfast this morning, and every moment of your future life are all equally real points in this four-dimensional block of space-time. Our sense of now is just a subjective spotlight moving through this block. The flow of time is a powerful illusion created by our consciousness as it lights up one moment after another. In this view, nothing ever happens. Everything simply is. So what is time? It is not the simple, steady river we thought it was. It is a flexible dimension that bends to gravity. It is a puzzle that disappears at the quantum level. It may be nothing more than the universe's unstoppable march toward disorder, a story told in the language of entropy. It might be a statistical illusion that emerges from complexity, or a structure built from the spooky threads of quantum entanglement. Or perhaps it is a frozen landscape, a block, where all moments exist forever. The clock on the wall, it turns out, isn't measuring a fundamental flow. It's measuring our own limited human relationship with the chaos, memory, and magnificent mystery of the cosmos. But our journey into the dark doesn't end there. We've looked at the vast emptiness, the spaces between the light. Now let us turn our attention to the most profound, the most absolute, and perhaps the most misunderstood objects in all of creation. We see them as points of utter destruction, the ultimate cosmic dead end. But what if we've been looking at them all wrong? What if the black hole is not a grave but a womb? What if it's not an end but the most violent and spectacular beginning imaginable? Let's begin with what we know. A black hole is born from the death of a truly enormous star. A star many, many times more massive than our own sun, which burns brightly for a few million years and then collapses under its own colossal weight. This collapse is so total, so unstoppable, that it crushes matter down past every known limit. It forms a shadow in space-time, a boundary we call the event horizon. This isn't a physical surface you could touch. It is quite literally the point of no return. It's the point where the pull of gravity becomes so strong that the fabric of space itself is falling inward faster than the speed of light. And at the very center of this collapse is the part we cannot understand. It is called the singularity. Our physics, the beautiful equations of Einstein that describe gravity so perfectly, they simply stop. They break. The math gives us answers like infinity, infinite density, infinite gravity, all crushed into a point with zero volume. This, of course, cannot be the final answer. It's a sign, a bright warning light from mathematics itself, telling us we do not know what happens here. Our understanding of the universe of space and time fails at this single impossible point. For decades, we treated this as a cosmic error, a place where information and matter go to be erased from the universe. But a new and much more profound idea has taken root. What if this breaking of physics isn't an error but a feature? The equations that describe the curve of space-time are famously complex, and they contain possibilities. Hidden in the math is a solution, a what-if, that has captivated scientists for a century. It's the idea of a bridge. What if the intense, focused gravity of the black hole doesn't just create a dead end, but instead punctures a hole through the fabric of reality. We call this a wormhole. Imagine taking a vast sheet of paper, our universe, and drawing two dots thousands of light years apart. To walk from one to the other would take a lifetime. But what if you could bend the paper folding space-time itself until those two dots are touching? And then what if you punched a tunnel, a shortcut, directly between them? This is a wormhole. It's a theoretical bridge connecting two different places, or perhaps even two different times. Is it possible that every black hole is the entrance to one of these tunnels? We don't know. Most theories suggest that such a bridge would be impossibly unstable, collapsing the instant anything tried to pass through it. But the possibility remains. The idea that this point of infinite collapse is actually a doorway, a gateway to somewhere or sometime else. This leads to an even more staggering thought. If the wormhole doesn't connect to another place in our universe, where does it go? Some physicists like Nikodem Poplawski have proposed a stunning hypothesis. What if the singularity at the heart of a black hole is a seed? Think about our own origin story. The Big Bang, our entire observable universe, all the galaxies, all the light, all the 13.8 billion years of time. It all began as a single point of unimaginable density and energy, which then banged or rapidly expanded to become the cosmos we know. Now look back at the black hole, a point of unimaginable density. What if they are one and the same? The theory is this: when a star collapses to form a black hole in a parent universe, the singularity it creates doesn't just sit there. It becomes the Big Bang for a new baby universe. This new universe is born inside the black hole, but it is not in the parent universe. It is a completely new bubble of space-time expanding into its own fresh dimension. It would have its own space, its own time. It would be impossible to reach or even see from the parent universe that birthed it. Think about what this means for us. What if our Big Bang was just the formation of a black hole in another older, vaster cosmos? What if our entire universe with its hundreds of billions of galaxies is just one of countless baby universes, blooming inside the event horizons of black holes in a multiverse we can never access? It's an idea that is both humbling and, in a strange way, comforting. It suggests the cosmos is a great cosmic tree constantly branching, with every black hole a potential new seed for a new reality. But this idea of creation comes with a deep, deep puzzle. It's a problem that troubled the great Stephen Hawking for most of his life. He called it the information paradox. The laws of physics at their most fundamental level insist on one thing: information can never be destroyed. It can be scrambled, burned, hidden, or rearranged, but it can never be truly erased. If you burn a book, you might think the information of the story is gone. But in theory, if you could capture every single particle of smoke, every single photon of light and heat, you could reassemble it. The story is still there, just in a very, very messy form. Black holes seem to violate this. If you throw that book into a black hole, it crosses the event horizon. It's gone, forever. Then over trillions of years, as Hawking himself discovered, the black hole slowly evaporates by leaking out a faint glow, which we call Hawking radiation. But this radiation is random. It's just thermal heat. It contains no information. It doesn't contain the story from the book. So where did the information go? Did the black hole truly fundamentally destroy it? This started what physicists called the Black Hole War, a decades-long debate about the very foundations of reality. And the solution that has emerged is perhaps the strangest idea of all. It's called the holographic principle. The holographic principle suggests that the information isn't destroyed, and it doesn't fall all the way to the singularity. Instead, as that book falls toward the black hole, its information is imprinted. It is encoded like a quantum watermark onto the surface of the event horizon itself. Imagine the event horizon as a vast two-dimensional hard drive. All the information of the three-dimensional things that fall into the black hole, the book, the star, the unlucky asteroid, is smeared out and stored on this two-dimensional boundary. So from the outside, the information is never lost. It's just flattened and saved. This concept is so radical that it has been extended to our entire universe. What if our reality, this vast three-dimensional world you live in, is actually a projection? What if all the information that makes up you and me and the stars is written on a distant two-dimensional boundary at the very edge of the cosmos? What if we are all just a hologram? The black hole isn't just a puzzle. It's a mirror showing us that reality may be profoundly different from how we perceive it. The math of black holes gives us one more beautiful mystery. If a black hole is a place you can only fall in to do, the equations allow for the opposite. A place you can only come out of. Yes, they are called white holes. A white hole is the time-reversed twin of a black hole. It is a singularity from which matter and light are constantly and unstoppably gushing out. Nothing can enter a white hole, you can only be ejected from it. We have never ever seen a white hole. They seem to be a purely mathematical fantasy. Or have we? Think about it. What is the Big Bang, if not a single point in time from which all the matter and energy in our entire universe came gushing out, a point that we cannot return to? Is it possible that our Big Bang was a white hole? This connects everything. Perhaps a black hole and a white hole are not separate objects, but two ends of the same wormhole. Matter falls into a black hole in a parent universe, travels through the tunnel and is born, exploding out of a white hole as a brand new baby universe. Our universe. The ultimate act of cosmic reissue cycling. The death of a star in one world becomes the birth of an entire cosmos in another. This leads to one final breathtaking idea. It's called cosmological natural selection. If universes are born from black holes, this sounds a lot like reproduction. And where you have reproduction, you can have evolution. The theory goes like this. Imagine a universe whose laws of physics are tuned to be very, very good at making black holes. Maybe its gravity is just right, or its stars are naturally massive. Because it makes many black holes, it reproduces more. It gives birth to many baby universes. Now imagine a different universe, one with sterile laws. Maybe its gravity is too weak and stars never collapse. That universe will never make a black hole. It will never reproduce. It will be a dead end. Over countless eons, as universes birth other universes, which universes will become the most common? The ones whose physics are perfectly optimized to create the maximum number of black holes. This theory offers a stunning explanation for why our universe seems so fine-tuned for life. We often wonder why the fundamental constants of nature, the strength of gravity, the charge of an electron are so perfectly balanced. If they were even slightly different, stars wouldn't form planets, wouldn't hold together, and we wouldn't exist. Perhaps the universe wasn't tuned for us. Perhaps it was tuned to reproduce, and we, our stars, our planets, our very existence, we are just a beautiful, magnificent side effect of a cosmos that is fundamentally built to create. So when you look into the darkness, do not see an ending. See a beginning. The black hole is not a monster. It is a gateway. It is the engine of eternity, the place where space and time are broken down only to be reborn fresh and new. We are the children of a universe that learned how to dream. And in every star that dies, it plants the seed of a new dream. And as we drift through these islands of light, these galaxies we've been exploring, we come to a realization that is, well, it's profoundly humbling. Everything we've talked about so far, the stars, the planets, the nebulae, the shimmering dust, even our own bodies, all of it, all the normal matter in the cosmos, only makes up about 5% of the entire universe. Just let that sink in for a moment. 95% of reality is completely invisible to us. It doesn't shine, it doesn't burn, it doesn't reflect light, it doesn't interact with us in any way we'd normally expect. Yet it dominates everything. We are living in a cosmos whose true nature is almost entirely hidden. We are in a very real sense strangers in our own universe. This vast dark majority is split into two separate magnificent mysteries. One is the glue that holds us together. The other is the force that is tearing it all apart. We call them dark matter and dark energy. Let's start with dark matter, which makes up about 27% of the cosmos. How do we know something is there if we can't see it? We see what it does, we see its ghost. In the 1970s, astronomers like Vera Rubin were studying galaxies, specifically how fast they rotate. They expected stars at the edge of a galaxy to move much slower than stars near the center. It just makes sense. In our own solar system, the outer planets like Neptune move far more slowly than the inner planets like Mercury, because the sun's gravitational pull is weaker out there. But that is not what they found. When they looked at spiral galaxies, they saw that the stars at the very edge way out in the galactic suburbs were moving just as fast as the stars near the core. This was a massive problem. The visible matter in the galaxy, the stars and gas we could see, didn't have nearly enough gravity to hold on to those fast-moving outer stars. By all rights, those galaxies should have spun themselves apart, flinging their stars into the empty void millions of years ago. The only way they could be held together is if the galaxy contained far more mass than we could see. A massive invisible halo of something, a dark matter halo, was gripping the entire galaxy, holding it together with its immense gravity. We see this invisible presence elsewhere too. Einstein told us that gravity or mass bends the fabric of space and time. So a massive object like a cluster of galaxies will act as a giant magnifying glass in space. It bends and warps the light from even more distant galaxies sitting behind it, creating strange, beautiful arcs, and multiple images of the same object. This is called gravitational lensing. Here's the thing: when we measure how much the light is bent, the visible matter in the cluster, all the shining galaxies combined, isn't nearly enough to account for the powerful lens we observe. Again, there has to be a huge amount of unseen mass providing the extra gravitational pull. This dark matter is the invisible culprit time and time again. So dark matter isn't just holding individual galaxies together, it's the very reason they exist at all. In the early universe, just after the Big Bang, matter was spread out almost perfectly, but almost is the key word. There were tiny microscopic fluctuations in density. Dark matter, being so much more abundant than normal matter, acted as the universe's primary gravitational force. It began to clump together, first forming a vast invisible network of filaments and nodes. Astronomers call this the cosmic web. It's like an enormous invisible scaffold stretching across billions of light years. The normal matter, the stuff we're made of, was then pulled by gravity into these massive pre-existing dark matter structures. It flowed into these invisible filaments like water flowing into a riverbed. And where the filaments crossed in the great cosmic intersections, matter pooled together to form the first stars and the first galaxies. When you see a map showing the distribution of galaxies in the universe, you're not seeing the real structure, you're just seeing the lights on the Christmas tree. The tree itself, the scaffold that dictates the entire grand structure of the cosmos, is the dark matter. But what is it? This is one of the biggest questions in all of science. We know it's not just dark clouds of normal matter because we would have detected it in other ways. It has to be something exotic, something entirely new to physics. Scientists have two leading candidates. The first are called WIMPs, which stands for weakly interacting massive particles. These are hypothetical particles that are heavy, but they barely interact with normal matter at all. Trillions of them could be passing right through you, right through the entire Earth every second, without ever leaving a trace. The other popular idea involves particles called axions, which are predicted to be incredibly lightweight, almost ghostly. Scientists have been running massive, deeply sensitive experiments in laboratories built deep underground, shielded from all other cosmic noise, just trying to catch a single fleeting glimpse of one of these particles. So far, nothing. The hunt continues. And as mysterious as dark matter is, it's nothing compared to the other 95%. If dark matter is the cosmic glue, there is another even stranger force doing the exact opposite. This is dark energy. For most of the 20th century, astronomers argued about the universe's expansion. Would it slow down and eventually collapse back on itself in a big crunch? Or would it slow down but have just enough energy to coast forever? Then in the late 1990s, teams of astronomers studying distant supernovae, exploding stars that act as cosmic lighthouses, made a discovery that shocked everyone. The expansion of the universe isn't slowing down, it's speeding up. Imagine throwing a ball into the air. You expect it to slow down because of gravity, maybe stop and then fall back. What these astronomers saw was like throwing a ball, watching it slow down, and then suddenly seeing it blast off into the sky, faster and faster as if it were attached to a rocket. Something is pushing the universe apart. This something is dark energy, and it makes up the vast majority of the cosmos, around 68%. We have almost no idea what it is. It seems to be a property of empty space itself. As space expands, more space is created, and with that new space comes more of this repulsive energy. It's a runaway effect. This discovery changes everything, especially when we think about the distant future. If this acceleration continues, our ultimate fate is one of profound isolation. As the universe expands faster and faster, other galaxies will be pushed away from us so quickly that their light will eventually not be able to reach us. They will vanish one by one over the cosmic horizon. The sky will grow darker until our own Milky Way galaxy is left alone, a single island of light in a vast, cold, accelerating emptiness. This is often called the Big Freeze. There is an even more dramatic, though less likely possibility. What if the strength of dark energy increases over time? This is a theory called the Big Rip. In this scenario, the repulsive force would eventually become so strong it would overwhelm gravity. First, it would tear galaxy clusters apart. Then it would rip the galaxies themselves to shreds. In the final terrible moments, it would overcome the forces holding solar systems together. Planets would be flung away from their stars. Then the planets themselves would explode. Finally, in the last fraction of a second, the force would become strong enough to tear atoms apart, ripping the very fabric of matter and space into nothingness. Now, is it possible we're wrong about all this? Some scientists are uncomfortable with dark matter and dark energy. They feel like we've just invented invisible fudge factors to make our equations work. They've proposed alternative ideas, most famously MOND, which stands for Modified Newtonian Dynamics. This theory suggests that we don't need dark matter, we just need to change the laws of gravity. Perhaps gravity just works differently on galactic scales than it does here in our solar system. But while MOND can explain some galaxy rotation curves, it struggles to explain gravitational lensing, and it has a very hard time explaining the cosmic web we observe from the afterglow of the Big Bang. The evidence for dark matter, as strange as it is, just seems to fit all the observations better. And so we are left in this remarkable place. We are thinkers, dreamers, explorers, living on a tiny speck of normal matter floating in a vast dark ocean. We are governed by forces we cannot see using laws we are only just beginning to understand. The universe is not just stranger than we imagine, it is perhaps stranger than we can imagine. When we look up at the night sky, galaxies appear as calm, majestic islands of light fixed in the darkness. We see static snapshots in torn magazines, perfect spirals, glowing ovals. But this stillness is an illusion, a trick of the vast timescales of the cosmos. In reality, these galaxies are in constant slow-motion motion. They aren't just drifting, they are part of a grand and chaotic cosmic dance pulled together by the inescapable grip of gravity. And very often this dance ends in a collision. This idea of a collision might bring to mind a violent high-speed crash, but a galactic merger is something entirely different. It's a process that unfolds over hundreds of millions or even billions of years. The first thing to understand is that galaxies are mostly empty space. The stars which contain most of the visible mass are incredibly far apart. If our sun were the size of a golf ball in New York City, the nearest star Proxima Centauri would be another golf ball in Chicago. So when two galaxies pass through each other, the stars themselves almost never ever hit. It's like two massive swarms of bees flying through each other. Individual bees will almost certainly miss. The stars are gravitationally disturbed, their neat orbits in their home galaxies thrown into chaos. They are flung into new long looping paths, often creating spectacular elongated streams of stars called tidal tails that stretch for thousands of light years. The shape of the original galaxies is completely scrambled and torn apart, but while the stars miss, the gas does not. Between the stars lie truly colossal clouds of cold hydrogen gas and dust, the raw fuel for new stars. These clouds are enormous, diffuse, and spread throughout the galactic disks. When two galaxies collide, these gas clouds crash into each other with tremendous force. This is where the creation part of the dance begins. As these massive clouds collide, they act like a cosmic shockwave. The gas is squeezed and compressed, creating pockets of extremely high density. In these newly dense regions, gravity has a chance to take over. The gas begins to collapse in on itself, clumping together, heating up and finally igniting the nuclear fusion that marks the birth of a new star. The result isn't just a few new stars, but a firestorm of creation. The collision triggers a galaxy-wide starburst, a period where new stars are formed at a rate hundreds or even thousands of times faster than normal. The galaxy lights up with the brilliant hot blue light of massive young stars. It is a stunning display of rebirth, a new generation of stars born directly from the chaos of the merger. We can see this happening right now. A classic example is the antennae galaxies. Looking at them through a telescope, we see two galaxies in the messy final stages of merging. We can clearly see the long tidal tails of stars, the two distorted cores, and most importantly, the entire region is dotted with bright blue knots of intense star formation, particularly where the gas clouds are colliding. It is a snapshot of creation fueled by destruction. This isn't just a fascinating event that happens far away, it's a preview of our own future. Our Milky Way is not alone. We are hurtling toward our largest galactic neighbour, the Andromeda Galaxy, at over 200,000 miles per hour. In about 4 billion years, our two massive spiral galaxies will begin their first pass, starting a merger process that will take billions of years more to complete. When this happens, our Sun, then a red giant, and the solar system will likely be thrown into a new distant orbit in the resulting giant elliptical galaxy, sometimes nicknamed Milkomeda. The familiar constellations will be gone, replaced by a spectacular chaotic night sky filled with new starbursts. But the stars and gas aren't the only things that merge. At the heart of both the Milky Way and Andromeda, like almost all large galaxies, sits a supermassive black hole, each with the mass of millions of suns. As the two galaxies merge, these two sleeping giants will sink toward the new centre of the combined galaxy. They will clear out stars in their path, lose orbital energy, and begin to circle each other in a tightening death spiral. In the final moments of their merger, these two supermassive black holes will be moving at a significant fraction of the speed of light, warping the very fabric of space and time around them. Their final collision will be an event of unimaginable power, sending out a tremendous blast of gravitational waves, ripples in space-time itself. These are the exact kinds of events that observatories like LIGO and Virgo are designed to hear, giving us a brand new way to observe the most violent processes in the universe. While galaxy collisions are slow and majestic, the universe also hosts collisions that are mind-bogglingly fast and violent. Among the most creative of these are the collisions of neutron stars. A neutron star is the leftover core of a massive star that has exploded. It's an object with the mass of our Sun crushed down into a sphere only about the size of a city. It is so dense that a single teaspoon of it would weigh billions of tons. Sometimes two neutron stars are born in a binary system orbiting each other. Over millions of years, they spiral closer, and just like the supermassive black holes, they eventually collide. This event, known as a kilonova, is one of the most extreme events in the cosmos. In the split second of their merger, they unleash a blast of energy and create conditions of temperature and pressure that are found nowhere else. This is the universe's ultimate forge. Inside normal stars, fusion can create elements like carbon, oxygen, and iron. But to create the heaviest elements like gold, platinum, and uranium, you need an environment flooded with neutrons that can be rapidly captured by atomic nuclei. This R process happens in the flash of a kilonova. The collision blasts these newly created heavy elements out into space. The gold in your jewelry, the platinum in medical devices, every atom of these precious heavy materials was forged billions of years ago in the cataclysmic seconds-long collision of two dead stars. From the slow, graceful merging of galaxies that sparks the birth of billions of new stars to the hyper-violent crash of neutron stars that forges the heaviest elements, its clear collisions are not the end. In the cosmos, collisions are the engine of creation, the mechanism of rebirth, and the source of the very materials that make our planet and ourselves. When you think of silence, what comes to mind? Perhaps it's a quiet room late at night when the world outside has finally gone to sleep. Or perhaps you imagine the vast, endless black between the stars. We call it empty space, the void, a great, silent nothing. It seems to be the very definition of absence, a place where nothing happens. This idea of emptiness is comforting in a way. It's simple. It's the backdrop, the canvas upon which the universe is painted. But what if I told you that this canvas is not blank? What if I told you that the silence is a roar and the emptiness is the most violent, chaotic, and powerful place in the entire cosmos? The nothing that we take for granted is in fact the most complex and generative something we have ever discovered. Tonight, let us redefine that emptiness. Let us journey into the storm that rages in the vacuum. In our quiet, human-sized world, a box with no air in it is empty. But in the quantum world, there is no such thing as empty. The fundamental rules of reality, the laws of quantum mechanics, simply do not allow for perfect stillness. There is a deep foundational restlessness to the universe. This empty space is more accurately called the quantum vacuum, and this vacuum is a seething, roiling sea of potential. It is a place where particles are constantly winking into existence, and then a fraction of a second later winking back out of existence. They are born from nothing and they return to nothing. These are not the solid particles you and I are made of like electrons and protons. These are called virtual particles. They exist in pairs, a particle and its antiparticle, and they are created by borrowing a tiny amount of energy from the vacuum itself. The universe has a strange loophole in its accounting books. It says you can borrow energy as long as you pay it back extremely quickly. The more energy you borrow, the faster you have to pay it up. So in every tiny patch of empty space at every moment, this storm is raging. A particle of light, a photon, appears and disappears. An electron and its opposite, a positron, burst into reality, find each other, and annihilate back into the void. It's a constant, furious, creative, and destructive foam of energy. This is the baseline of reality. This is the true nature of nothing. Now, this might sound like a beautiful abstract fantasy, a philosopher's dream, but it is profoundly measurably real. We have seen the effects of this storm. We have physical proof. It comes from an elegant experiment known as the Casimir effect. Imagine you are in a perfectly violent, empty vacuum. You take two metal plates, perfect mirrors, and you bring them incredibly close together. So close that they are just millionths of an inch apart. According to our old classical ideas of emptiness, nothing should happen. They are just two plates floating in a void. But something does happen. The plates are pushed together by an invisible force. Why? Because of the storm. The quantum vacuum is raging all around the plates, pushing on them from the outside with the full force of its virtual particle chaos. But between the two very close plates there isn't enough room. The tiny gap acts as a filter. Only virtual particles of a very specific, very small wavelength can fit inside that gap. This means there is more storm pushing on the outside of the plates than there is pushing on the inside. The universe itself, the energy of nothing, presses the plates together. We have measured this force. It is the physical, undeniable fingerprint of the vacuum's energy. It is the universe telling us, I am not empty. This vacuum does more than just push things around. It gives shape and substance to our entire reality. You and I, we have mass. The chair you're sitting on, the air you're breathing, the planet beneath you, it all has mass. It feels solid. But why? Why do some particles have mass while others, like particles of light, have none? The answer once again is found in the vacuum. Imagine that all of space everywhere, even inside your own body, is filled with an invisible field. Think of it like a kind of cosmic molasses, a sea of white transparent energy that permeates everything. This is called the Higgs field. When the universe was born, this field was off. But as the universe cooled, the field turned on, settling into its lowest energy state. And crucially, its lowest energy state was not zero. The empty vacuum became filled with the Higgs field. Now particles that travel through this field interact with it. Some, like photons of light, don't feel it at all. They zip through at the speed of light, massless and free. But other particles, like electrons or the quarks that make up protons, do interact with it. As they try to move, the Higgs field drags on them. It resists their motion. And this resistance, this stickiness from the vacuum itself, is what we experience as mass. Without the energy of the vacuum, without the Higgs field filling all of empty space, nothing would have substance. The fundamental building blocks of your body would be massless specks of energy flitting about the cosmos. There would be no atoms, no planets, no stars, and no you. We are given form and reality by the nothing we thought was so empty. So the vacuum has energy. We've proven it with the Casimir effect. It gives mass via the Higgs field. The next logical question a scientist asks is, okay, how much energy? And this is where we run into the single greatest mystery and the single greatest failure in all of physics. When our theorists used quantum mechanics to calculate the total energy density of the vacuum, summing up all that virtual particle chaos, all that fizzing and boiling, they got a number. It was not a small number, it was in fact the largest number that has ever appeared in science. It was an energy so vast, so staggeringly enormous that it should be an overwhelming dominant force in the cosmos. If the vacuum truly had this much energy, the universe should be expanding so fast that no two atoms could ever find each other. No stars or galaxies could ever have formed. But that's not what we see. We look out at the universe and we do see that space is expanding. In fact, it's accelerating, pushed apart by a mysterious force we call dark energy. And this dark energy is the energy of the vacuum. We have measured its value, and the value we measured is tiny. It's a whisper. When you compare the predicted energy of the vacuum from our theory with the observed energy of the vacuum from our telescopes, the numbers don't just disagree. They disagree by a factor of 1, followed by 120 zeros. This is not a small error. This is the cosmological constant problem. It is by far the most profound disagreement between theory and observation in the history of human thought. Our best theories of the universe are wrong in their most fundamental prediction by a margin that is larger than any other number in science. It means we are missing something vast, something essential. We do not understand the vacuum. We do not understand nothing. Is there some other unknown law of physics that is cancelling out almost all of that energy, leaving just that tiny residue we call dark energy? Is our understanding of gravity or quantum mechanics or both completely wrong? The answer is hidden right in front of us in the empty space between your eyes and the screen in the silence between the stars. This mystery leaves us with an even more unsettling speculative thought. We know the Higgs field fills the vacuum, giving us our laws of physics and the property of mass. We assume that the energy state of this field is at its lowest possible point. We assume it's stable. But what if it's not? What if our universe is in what physicists call a false vacuum? Imagine a ball resting in a small dip on the slope of a very deep valley. This ball is stable for now. It's in a local minimum, but it is not at the true bottom of the valley. If someone were to give that ball a hard enough push, it would roll out of its comfortable dip and plunge all the way down to the true minimum, the real bottom, releasing a huge amount of energy as it went. Our universe might be that ball resting in that dip. The value of the Higgs field and all the laws of physics that depend on it might just be a temporary state. If a random quantum event somewhere out in the deep cosmos pushed a tiny patch of space over the edge, it would fall to this new true vacuum state. This would create a bubble of a new reality with new laws of physics, and this bubble would expand outward in all directions at the speed of light. As it washed over our galaxy, our solar system, our planet, everything would be rewritten. The very nature of mass and energy would change. It would be the end of our universe as we know it, and the birth of a new one. It's a sobering thought, that our entire reality so solid and permanent to us might be perched precariously on a cosmic ledge. But this too is the power of the vacuum. It is not just a passive void, it is a place of infinite potential. It is the engine of mass, the source of the greatest mystery in science, and perhaps a ticking clock for reality itself. From this chaos, this quantum foam of particles appearing and disappearing, our entire universe may have been born. One single random fluctuation of virtual particle that instead of disappearing borrowed enough energy to inflate into the Big Bang. Everything we see, every star, every galaxy, every person, every dream, all of it springing forth from the emptiness we so misunderstood. The void is not an absence, it is the womb. It is the creative, chaotic and powerful storm from which all of existence is born. As you drift off to sleep, let your mind rest in that deep, dark, fertile emptiness. The silence that is not silent at all. The nothing that is in truth the seed of everything. When we look up at the night sky, we often talk about looking out into space. But the most profound truth of astronomy is that we are not looking out, we are looking back. We are not seeing the universe as it is right now, but as it was in the past. This isn't a metaphor or a science fiction idea, it is the fundamental reality of observation, and it transforms the sky from a static picture into a deep unfolding history. This entire concept hinges on one simple finite number, the speed of light. Everything we see because light travels from an object to our eyes. In our daily lives, this seems instant. We don't notice the delay in seeing a friend wave from across the street. But light, while incredibly fast-moving at approximately 300,000 kilometers every second, is not infinitely fast. It takes time to travel. In the vastness of space, these travel times are not just measurable, they are enormous. Let's take a journey. The moon is our closest celestial neighbour. The light we see reflecting off its surface takes about 1.3 seconds to reach our eyes. When you look at the moon, you're seeing it as it was 1.3 seconds ago. This is a tiny delay, but it's real. The light from our sun takes about 8 minutes to cross the 150 million kilometers to Earth. If the sun were to suddenly and impossibly vanish, we would continue to see it shining and feel its warmth for 8 full minutes before we were plunged into darkness and cold. We are always seeing the sun as it was 8 minutes in the past. Now let's leave our solar system. The nearest star system to ours, Alpha Centauri, is about 4.2 light years away. This unit of measurement, the light year WAS, isn't a measure of time, but a measure of the immense distance that light travels in 1 year. It means the light we see from that star tonight began its journey 4.2 years ago. We are seeing the star not as it is today, but as it was when a high school freshman today was just starting elementary school. This effect stretches to staggering scales. When you see the Andromeda Galaxy, our nearest major galactic neighbour, it appears as a faint fuzzy cloud in the night sky. That cloud is 2.5 million light years away. The photons, the particles of light hitting your retina tonight, began their journey 2.5 million years ago. At that time, modern humans did not exist. Our early ancestors, like Homo habilis, were just beginning to walk the Earth. We are looking at an object so far away that its light has been travelling since before the dawn of our own species. This time machine effect is the entire purpose of modern telescopes. They are not just magnifying glasses, they are tools for deep time archaeology. The James Webb Space Telescope, for example, was built specifically to exploit this. Its goal is to look so far away that it can see the cosmic dawn, the light from the very first stars and galaxies that ever formed. When the Webb telescope captures an image of a galaxy 13.5 billion light-years away, it is seeing a snapshot of that galaxy as it was 13.5 billion years ago, when the universe itself was just a baby only a few 100 million years old. We are watching the universe ignite. There is a major challenge in seeing this ancient light. The universe has been expanding for its entire 13.8 billion year history. This expansion isn't like an explosion of things through space. It is the stretching of space itself. Imagine a light wave as a line drawn on a balloon. As you inflate the balloon, the line itself stretches and gets longer. The same thing happens to light travelling through expanding space. As the light from a distant galaxy travels billions of years to reach us, the space it is crossing is stretching. This stretching action pulls the light waves, making them longer. In the visible spectrum of light, the longest waves are red. This stretching of light from distant objects is therefore called redshift. The further away a galaxy is, the faster space is expanding between it and us, and the more its light is redshifted. For the very first, most distant galaxies, their light has been stretched so much that it is no longer even visible light. It has been stretched all the way into the infrared spectrum, which we perceive as heat. This is precisely why the James Webb Space Telescope is an infrared telescope. It is designed to see this ancient, stretched, redshifted light from the beginning of time. This time delay phenomenon creates a profound illusion in our night sky. We are not seeing a single instant. We are seeing a collage, a mosaic of different times all layered on top of each other. In a single glance, your eye captures the moon from 1 second ago, Jupiter from 40 minutes ago, the North Star from over 400 years ago, and the Andromeda Galaxy from 2.5 million years ago, all at the same now. This also leads to a strange and somewhat sad realization. Many of the stars we see in the sky may already be dead. Consider a giant star like Betelgeuse in the constellation Orion. It is about 640 light-years away. We know that a star of its massive size will end its life in a spectacular explosion called a supernova. Astronomers believe Betelgeuse is near the end of its life and could explode soon in cosmic terms any time between tomorrow and the next 100,000 years. But because it is 640 light-years away, it is entirely possible that Betelgeuse already exploded. It could have exploded 500 years ago in the time of Leonardo da Vinci. We would have no way of knowing. We would still see it shining peacefully in the sky tonight, a ghost of light, and we would have to wait another 140 years for the light from its death explosion to finally reach our eyes. The night sky is filled with these phantoms. So how far back can we see? Is there a limit? Yes, there is. The universe is about 13.8 billion years old. This means the absolute furthest we could possibly see is 13.8 billion light-years away, because light from anything further than that simply has not had enough time to reach us yet. This boundary defines our observable universe, but we can't even see all the way back to the Big Bang itself. For the first 380,000 years of its existence, the universe was not dark, it was blindingly bright, but it was also a fog. It was so hot and dense that it was an opaque plasma like the inside of the sun. Light could not travel freely. It would immediately slam into a particle and scatter. You could not see through it. Then after 380,000 years, the universe cooled enough for atoms to form. The fog suddenly cleared and the universe became transparent. The light that was present in that exact moment was finally set free, and it has been travelling across the universe ever since. We can still see this light today. Because of the 13.8 billion years of expansion, this intensely hot, bright light has been redshifted, stretched all the way down from visible light past infrared and into the microwave spectrum. This is the cosmic microwave background, or the CMB. It is the afterglow of creation, the oldest light we can ever see. It is a wall to our vision. When you look at the static snow on an old analog television, a small percentage of that interference is your television set picking up the faint ancient echo of the Big Bang itself. This cosmic history, this journey of light and time, is not just an external story, it is our own. The universe began with only the simplest elements like hydrogen and helium. The carbon in your brain, the oxygen in your lungs, and the iron in your blood did not exist. These heavier elements were created or fused inside the blazing hot cores of massive stars. Those stars lived for millions or billions of years and then died in massive supernova explosions, scattering those newly forged elements across space. That stardust eventually cooled, clumped together, and formed new stars, new solar systems, new planets, and on at least one planet us. The atoms in your body are ancient. They are the recycled remnants of stars that died long ago. The history we see in that ancient light is not separate from us. It is our own family tree. We are in the most literal sense made from the same history that we are observing. We are the universe becoming aware of its own long and incredible past. We've spent so much time on our journey together, looking up at our sky, trying to understand this vast singular home of ours. We've charted the galaxies, we've measured the ancient light from the cosmic dawn, and we've mapped the great cosmic web that connects everything. It feels impossibly large, perhaps even infinite. But what if this all of it, every star, every galaxy, every speck of dust we can ever hope to see is just one single page in an infinitely large library? This is the central mind-bending idea of the multiverse. It is the hypothesis that our universe, the one we call home, is not the only one. It suggests that we are just one bubble in a vast cosmic ocean of other bubbles, other universes. It's an idea that stretches the very definition of everything and forces us to confront our own place in a reality that may be vastly larger than we ever dreamed. How could such a thing even be possible? Where would these other universes be? One of the most compelling ideas comes from the very theory that explains our own beginning, cosmic inflation. We believe our universe began with an incredible explosive burst of expansion. In a tiny fraction of a second, the universe stretched from a microscopic point to something astronomically huge. The theory of eternal inflation takes this one step further. It suggests that inflation as a high-energy process never truly stops. Imagine a massive, eternally expanding ocean of this inflationary energy. In some pockets of this ocean, the energy cools down, the inflation stops, and the energy converts into matter and radiation. When it does, a new universe, a bubble universe, is born. This pocket breaks off from the inflationary ocean and begins its own life with its own Big Bang. Our universe would be one of these bubbles, but outside our bubble in the vast ocean, the inflation continues, stretching the space between the bubbles at an unimaginable rate. And in that expanding ocean, new pockets are constantly cooling down, forming new bubbles, new universes, each with its own Big Bang. In this picture, the creation of universes isn't a one-time event. It's a continuous, never-ending, fractal-like process. Our Big Bang wasn't the Big Bang, it was just our Big Bang. If there are other universes, are they like ours? Do they have stars, planets, and chemistry? Or are they completely alien, governed by different rules? This is where another fascinating and deeply complex idea comes into play: the string theory landscape. String theory is an attempt to be the theory of everything. It proposes that the fundamental building blocks of reality aren't tiny points but tiny vibrating strings of energy. The way a string vibrates determines what kind of particle it appears to be. But for this theory to work mathematically, it requires extra dimensions of space. Dimensions we can't see curled up, possibly small all around us. The string theory landscape is a way of visualizing all the possible ways these extra dimensions can be folded or shaped, and the number of possibilities is staggering. It's estimated to be 10 to the power of 500. That is a 1 followed by 500 zeros. It is a number so large that we cannot truly comprehend it. There is not enough matter in our entire observable universe to even write that number down. Each of these possibilities, each unique way of folding the dimensions, would result in a universe with its own unique set of physical laws. In one universe, gravity might be much stronger, crushing everything into black holes. In another, electrons might have a different charge, making atoms impossible. In the vast majority of them, the laws of physics would be chaotic and sterile, unable to produce any kind of complexity. This massive landscape of possibilities helps address a very deep puzzle. Why is our universe so perfectly, so finely tuned for life? The values of the fundamental constants, the speed of light, the strength of gravity, the mass of a proton are all balanced on a razor's edge. If any of them were just slightly different, the universe would be dead. Stars wouldn't form. Carbon atoms, the basis of our biology, wouldn't be stable. Life would be impossible. Why did we get so lucky? The anthropic principle offers a possible though controversial answer. It flips the question around. It suggests we shouldn't be surprised to find ourselves in a universe that can support life, because if it couldn't, we wouldn't be here to ask the question in the first place. If there are 10 to the power of 100 universes in the landscape, each with random laws, it's no longer surprising that at least one of them, ours, happens to have the right combination for complexity and consciousness to emerge. We are here looking out at the cosmos because we live in one of the rare, lucky universes where the laws of physics allowed us to evolve. It's not that the universe was designed for us, it's that we could only exist in a universe that had these specific life-permitting properties. There is another completely separate path to a multiverse one that comes not from the grand scale of the cosmos, but from the bizarre rules of the subatomic world. This is the many worlds interpretation of quantum mechanics. Down at the quantum level, reality is a blur of possibilities. A particle like an electron doesn't seem to have a definite position until we measure it. Before that, it exists in a superposition. It could be here, or it could be there all at the same time. The traditional view says that when we measure it, this wave of possibilities collapses and the particle randomly chooses one reality. The many worlds interpretation is more radical. It says the wave never collapses. Instead, every single time a quantum event has more than one possible outcome, the entire universe splits. In one universe, the particle is here. In another brand new universe that instantly branches off, the particle is there. Every quantum coin flip, every radioactive decay, every choice splits the world. This means you right now are splitting into countless versions of yourself. There is a version of you that decided not to continue on this journey. A version that chose a different path this morning. This isn't a universe far away in space. It's a branching of our own reality, creating parallel worlds that are constantly multiplying, all existing simultaneously, just out of reach. The implications of any of these multiverse theories are profound and frankly a bit dizzying. First, there is the implication of cosmic isolation. If the bubble universes from eternal inflation exist, they are expanding away from us faster than light. The space between us is stretching too fast to ever cross. We can never visit them. We can never receive a signal from them. We are in every practical sense completely and totally isolated in our own bubble. The same is true for the many worlds interpretation. Those other branches of reality are parallel to ours. We cannot interact with them. This forces us to ask, what is the value of questioning? If we can never prove these other worlds exist, are they even science? Or are they just fascinating philosophy? Perhaps the value isn't in finding a concrete answer. Perhaps the value is in what the question itself does to our perspective. Thinking about the multiverse forces us to confront our own cosmic significance or lack thereof. If there are infinite copies of us, what is the value of this one? If our universe is just one random outcome among a near infinite number, what does that make our struggles, our search for meaning? But it can also be liberating. It tells us that our universe, this little patch of reality, is our responsibility. The fact that this universe, the only one we can ever know and touch, happens to have the laws that allow for stars, for planets, and for conscious minds to wonder about it all, that is an extraordinary thing. It makes this existence, this one stream of consciousness, unbelievably precious. The act of asking, are we alone in the cosmos? Or is our cosmos alone? Expands our own minds, even if the final answer remains just beyond our grasp.